Before we begin our study of circuit analysis, we need to do a review of electrostatics to motivate the definition of voltage and current. Alright, so what we have to do is we have to review this thing called electric charge. And you should recall from physics that electric charge is a physical property of matter. Right? And we have two types of charges. We have a positive charge and a negative charge. And this physical property is given the SI unit of Coulomb. Right? So from a microscopic viewpoint, charge arises from a fundamental conserved property of these subatomic particles, namely electrons and protons. Now, electrons and protons are particles that have a small amount of charge to them, namely 1.6 times 10 to the negative 19 coulombs for the proton, and electrons are negatively charged with the same magnitude of charge. So they have a charge of negative 1.6 times 10 to the negative 19 coulombs. Because this is a conserved property, the conservation of charge tells us that electric charge can be distributed between one place and another. But if we look at a closed system, the sum of the positive and negative charges within that closed system can't change unless we add or remove particles from the system. Kind of makes sense. We can't create or destroy electric charge. We can only move it around. All right. Now, we can get objects that become negatively charged if they have more electrons than protons in them, or we can get objects that become positively charged if we have a removal of electrons, or namely fewer electrons than protons. If there's a balance between protons and electrons within an object or within a given area, we have a neutrally charged object. Now, an attraction force is exerted between both positively and negatively charged objects. So if they're opposites attract. So if we have oppositely charged particles, there's going to be an attraction force exerted between the two of them. And if the two particles or two objects have the same sign of charge, there's going to be a repulsive force. So two negatively charged objects will repel each other, and two positively charged objects will repel each other. Also, an attraction force is exerted between a neutral object and any charged particle or object. So both a negatively charged object or a positively charged object will experience an attractive force with a neutral object. Now note that this has to be a neutral object, not a particle, for this to be true. All right, and the magnitude of and direction of the electric force that's exerted between two charges can be calculated using Coulomb's law, where Q1 and Q2 are the magnitude of charge associated with the two particles that we're or objects that we're looking at. Okay, so we see a couple things here. We see that the force here is a vector. It has to be expressed in 2 or 3 dimensions, and it's proportional to the magnitude of charge. We also have to include the sign, whether it's a positive charge or a negative charge here for Q1 and Q2. And also that's going to be divided by 4 pi times this permittivity of free space right here. Now we can combine 1 over 4 pi times the permittivity of free space and combine that into this thing called the Coulomb constant right here. Just to simplify the Coulomb's law a bit. Alright, that's also inversely proportional. That product there is inversely proportional to the distance between the two charged objects. And to get the direction on that, we have to multiply that by a unit vector that points in the same direction as the vector, the distance vector between the two objects. Okay, so this is a unit vector that tells us the direction that in which the force acts. This is the magnitude of the vector squared. So this is the distance squared. This is the direction that that force vector points. Okay, so now imagine, if you will, that instead of having two charged particles, we have let's say, a positively charged particle here. We have a positively charged particle here, and we have a negatively charged particle here. Now, if we want to determine the net force results from having this from having this charged object here and this charged object here and this charged object here, what we'll have to do is we have to look at the total sum of the forces acting on this particle. So first we have to calculate the force that results from the interaction between these two charged particles. All right. Since this is a since they are both of the same sign, this particle or this object right here is going to experience a net. It's going to experience a force, a repulsion force, in this direction. And then we have to also consider the force that results from the interaction between these two objects. All right. Since this is a oppositely charged sign, a negative charge, whereas this is a positive charge, there's going to be an attraction force between these two. So the net result is that we're going to have a force exerted on this positive charge that goes in that direction. Now the net, or the total force that acts on this object, is the vector sum of these two interaction vectors. So we have a force on object 1 due to object 2. That's a vector. And we also have the force on object 1 due to object 3 that points in that direction. So to come up with the total force that's exerted on object 1, we have to sum the two vectors together. So the total is the vector sum of F12 plus, it's the vector sum of F12 plus F13. All right, and we can simplify that, or we can rewrite that, express that as the principle of superposition. All right, so this basically says the same thing. If we have multiple charges, to get the total force that is exerted on one charge, we have to sum all of the effects of all of the charges up. Okay. Now we're going to move on to the concept of an electric field, and this electrostatic field or electric field is generated in the vicinity of an electrically charged object. This electric field is the tendency for these charged objects to exert a force on other electrically charged matter. So the electric field is defined as the force per unit charge that would be experienced by a stationary positive point charge at a location in the field. Alright, so again, let's read that again. The electric field is defined by the force per unit charge that would be experienced by a stationary positive point charge at a location in the electric field. Alright, so the SI unit for electric field strength is going to be force per unit charge, or newtons per coulomb. Alright, a way to visualize that, again, is remember that if we have a collection of say a positively charged object, right? We have a collection or an absence of electrons, so we get a net accumulation of positive charges. All right, these positive charges are going to tend to exert a force on a small positive charge, and what we can do is we can imagine taking this small positive charge and moving it around, and using Coulomb's law, we can determine in what direction and how much force would be exerted on that small charge due to this larger positive charge. Right? So we can look out here. Since it's further away, we'd have a smaller magnitude. All right, and this becomes for us the electric field. All right. Now, if we didn't put these small positive point charges here, this electric field would still exist because this object, this positively charged object, which also could be a negatively charged object, is still going to tend to exert that force on this small stationary point charge, whether or not there's a charge there. Okay, so we've gone through that. So the electric field is essentially tells us how much force would be exerted per unit charge if we add a small charge into a system. All right, and this electric field exists near a charged object, and it's independent of that small charge. So The electric field still exists even if we don't put a charge there. And we can calculate the magnitude and the direction near this of this field near the point charge using essentially Coulomb's law. All right, so Coulomb's law, if we flip back a couple of slides here, right, tells us about this force. Well, we're going to take this force, and to get the electric field, we divide by the magnitude of this small point charge, which leaves us with one charge, namely the larger charge that we're looking at the field around, over this stuff right here and this unit vector. All right. So what we can do is we can visualize the electric field, or the force per unit charge, by computing the electric field strength at different points around a charge or a system of charges. And because this is because the electric field tells us the force that would be exerted on a small stationary positive point charge, the vectors are always going to point away from positive charges and always point towards negative charges. So you can see for a couple of different systems of point charges here how the electric field is going to look. We can also visualize this using electric field flux lines. So what we can do is we can draw lines that are tangent to the electric field vectors, and these field flux lines indicate the direction of force that would be experienced by a very small positive particle that's placed into the field. All right, so if we put a small particle somewhere in this field, we can determine the direction that that force would go. All right, and that comes about from drawing lines tangent to the lines of the electric field lines. Right. Okay. Of course, we don't live in a two-dimensional world. We live in a three-dimensional world. So in this three-dimensional world, there's this thing that we define as being a point charge. So in this three-dimensional world, these electric field lines extend radially in all three dimensions. All right, and this is kind of how we would visualize that. Right, there's a small point charge there, and anywhere around that, there's going to be radiating out of that small spherical point charge. There's going to be radiating the electric field, and we can determine the electric field strength anywhere around that charged particle in three dimensions using this vector formula right here. All right, so again, it looks a lot like Coulomb's law. All right, now imagine, if you will, that we take some positively charged point charges and we look at the field lines, and what we do is we start taking these positive point charges and bringing them closer and closer together. Okay, so if we look at the field lines, as we start bringing these particles closer together, or these charges closer together, we're going to get bending because of the principle of superposition. We're going to get bending in the field lines. Right, and I'm going to start doing this. All right. And you can imagine that as we start bringing these closer and closer together, we're going to have less of this bending motion occurring, or this, less of this bending in the field lines. So if we really smush them in tightly with each other, we're not going to see a lot of the effect of that bending, and eventually what we could do is we could think about what happens in the limit when we fill all of this space with nothing but positive charges. And when we do that, from this, remember that these point charges are, the field lines are radiating out in all directions. So it would, in addition to that direction, it would be going up and all the way around radially. And what that does is that creates for us this concept of line charge. So when we have charge that's distributed along a line, we have this thing called a line charge, and the field lines extend radially in three dimensions from this line. And we can, again, compute around this small rod, or this line here, the electric field strength anywhere at some distance away from that rod. Right? What we could do now is we can imagine taking those rods and smushing them together, right? Much in the way that we took those point charges and brought them close to each other. So if we take the Line charges, again, we'll envision that they're positively charged, that have radial field lines extending in 3 dimensions all around this rod. And we take another positively charged rod, or line charge, and we start bringing the two of them close to each other. We're going to get the same bending effect going on, and what's going to happen is the field lines are going to start pointing out towards you, towards the camera, and away from the camera. Okay, in the opposite direction. And the closer and closer we bring them, the more intense we're going to have the field lines going out towards the camera and away from the camera. All right? And that forms the basis for this thing called the sheet charge. All right? And the sheet charge is how much, when we have charge that's distributed on a flat plate or a flat plane. And the field lines are going to extend perpendicular to the plate, and the field magnitude in this case then becomes independent of the distance. All right? And we can see that from this electric field strength calculation right here. All right. Now, in electronics, we're going to often refer to the combination of two oppositely charged parallel plates. Well, if we have two oppositely charged parallel plates, we have the superposition of two sheet charges. All right, so these two these two plates, oppositely charged parallel plates, we're going to have, we can calculate the electric field strength between those two plates if we know the total amount of charge that's accumulated on both the positive plate and the negative plate, and the distance, the separation distance between the, the direction at which they're separated. Because remember that sheet charges, the electric field strength does not depend on the distance away from, how far away they are from each other. It only depends on the direction that they are away from each other. So in that manner, we can compute the electric field strength between two positively charged plates. Okay, now with that, we can compare Newton's law to that of the law of gravitation. And the only difference here that we see, with it's of the same form, it's some constant multiplied by the two, either the mass of the two objects or the charge on the two objects, and it's proportional to the inverse of the squared distance between the two objects. So we see that gravity is very similar to Coulomb's law. The only difference with gravity is that, at least so far, we don't have a negative mass, or we don't have an anti-gravity particle that we are aware of. But fundamentally, they look very much the same. And we can use that analogy to talk about and compare the two concepts. All right. So in this gravity analogy, we have a mass, and a small mass is going to experience a force in the direction of a larger mass. That's similar to the fact that a small charged particle is going to experience a force in the presence of an electric field. Okay, so we have the gravitational field here being analogous to the electric field. So mass and charge are analogous, and the gravitational and electric fields are analogous to each other. Now, where this helps us out is that this brings us to the concept of work. All right, if you'll recall from statics and dynamics that we can characterize the potential energy of an object by its location in the field, in the gravitational field. Basically, we say an object has high potential energy if it's very high above the ground or the reference point, and we say it has a very low potential energy if it exists or it's positioned at the reference point. Okay, similarly, since we're working with positive charges, we're referencing everything to a positive charge in an electric field. We say it has a positively charged object will have a high potential energy when it's close to other positive charges, and it has a low potential energy when it is close to where it wants to be near a negatively charged object. Similarly, for negatively charged particles or objects, they have a low potential energy when they are at their point of attraction, when they're at the positive plate that they want to be near. And similarly, they have a high potential energy when they're far away from the positive plate. Now, this leads us to this concept of electrical work, because from dynamics we know that work is force that's applied through a distance. So the work that's required to move a charge in an electric field is defined as the force dotted with the vector distance that it travels in the same direction of the field. All right, so we can replace this force right here with the definition of the electric field, right? Remember that for the exerted force is the charge on the particle multiplied by the strength, or the vector strength of the electric field. All right, since the particle, the small particle right here, has a fixed charge associated with it. Note that there's a negative sign here now. Since it has a fixed charge associated with it, we can pull that outside of this integral and only worry about the electric field vector and the direction vector in which it is moved. And this work right here is an expression of the potential energy of that positive or negative charge. So positive work decreases the potential energy, okay, and this is what happens when we bring attractive charges together, or we separate two like charges, and what we say is that the field does the work on the charge. Positive work has to increase the potential energy, and that means that work needs to be put into the electrical system to separate attractive charges or bring two like charges closer together. And in this case, work is done in the direction opposite of the field. Okay. Also note that, just like from statics and dynamics, there's the work done to move a charge a distance of r2 minus r1 in the same direction as a uniform field is going to be negative QED. So the reason we work with parallel plates is because the distance, the separation distance between them, doesn't matter, all right, and we get this constant that's really only proportional to how far we're going to move that particle in the charged field. All right. Also note that, just like from statics and dynamics, no work is done when we try to move a charge perpendicular to the electric field, and that arises because of this dot product right here. Work is only done in the direction of the electric field. All right. Now, this finally leads us to this concept of voltage. All right, voltage is an expression of work. All right, voltage is when we move charges against an electric field, or we separate charges, this requires work. All right, voltage is how we describe the work and the strength of an electric field. All right, and essentially how it is what it does is it expresses the work that's required to move 1 Coulomb of charge, 1 unit, or 1 Coulomb of charge from one point to another point in an electric field. All right, so the further we move it, or the larger all of the charge, or the larger the charge, the more work, the more voltage that we get. All right, so this is the differential voltage per differential charge, or how much work has to be done, it's the differential work per differential charge, or how much work has to be done per unit charge to move it in an electric field. All right, since it's work per charge, or energy per unit charge, it's expressed in terms of joules per Coulomb, which is the same thing as a volt. Okay, we can kind of go back to the gravity analogy now, and look at how voltage and work are analogous to each other. Now, from our studies in dynamics, we know that if we take, now this is a silly example in a way, but if we take a bag that's full of 1 pound force rocks, and let's say we have 20 of them, all right, and say I want to move that, I want to pull this bag of rocks up a distance of 1 foot. All right. If I want to lift it up a distance of 1 foot, how much work has to be done? Well, we know that work is force applied per unit distance. All right, and we're going to have to lift this up against gravity. We're going to have to apply 1 pound per rock, so that would be a total of 20 pounds force per foot, right? Or multiplied by that 1 foot distance. So we're going to have 20 foot-pounds of work to lift this bag of rocks up. Now, voltage, on the other hand, does not ask this question. It's like if we're going to the analogy is that that voltage is not how much work needs to be done overall to move all of these charges, all of these positive charges, from one place to another in an electric field. It answers the question of how much work has to be done per unit charge that we have, or per unit Coulomb, to move these charges in this electric field. Okay, namely, that's like saying how much work has to be done per unit rock in this bag. All right, so voltage here, the voltage, the analogy to voltage would be we have to apply 1 foot-pound of force per rock to move the entire bag of rocks up 1 foot. And so voltage is an expression of the potential energy, or the energy that we need to put into a system to move the charges per unit charge. All right. Okay, so we can envision connecting a source of electrical energy between two parallel plates, and what this voltage supply, like we've used in lab, is going to do is it's going to separate or move charges from one plate to another. Now, as it's separating these charges from, it's essentially what it's going to do is pull electrons from a neutrally charged plate right here, and do work on those electrons to bring them down to this neutral plate right here. So that results in a net positive on the top plate and a net negative on the bottom plate. All right, so what it does is we're using energy to separate the charges and move them from one plate to another. And the voltage is the measure of the potential energy difference per unit charge between the charges on those plates. All right, how much energy, how much work has to be done per unit charge to move the electrons from this neutral plate to this neutral plate. All right, so the greater the voltage, the more work is being done, and namely the greater number of charges that are being moved from the positive plate to the negative plate to create or enhance the electric field strength. All right, so again, the big takeaway from all of this is that voltage tells us about the potential energy of the particles, of the charged particles in a system. Right? If we have an accumulation of charged particles of the same charge, they do not want to be located near each other. So we have to do work, or we have to apply energy to keep them in a position that they do not want to be in.